Hello, class. Today we're going to discuss the electric field. Previously, we just discussed about the electric force on a charged particle, but now we're going to discuss that the electric field strength can be calculated at a point around a charged particle. One equation to calculate the electric field strength is the electric force divided by the charge, and the SI unit for electric field is Newton per Coulomb. Here's an artistic way of describing electric fields by drawing arrows around the charged particles. For positive particles, the electric field radiates outward, and for negative charged particles, the electric field lines point inward. The number of field lines starting or ending on a positive or negative charge is proportional to the magnitude of that charge. Another thing to point out is that the further the lines are apart, the weaker the electric field strength. So this pictorial drawing shows that the electric field strength is becoming weaker the further away you are from the charged particle, which makes sense. Another equation for electric field strength is kq over r squared, which is the result of when you plug in the equation for electric force. Okay, I think we're ready for our first example. We want to calculate the magnitude and direction of the electric field at point P, which is 30 centimeters to the right of the point charged particle, which is -3 times 10 to the -6 coulombs. We'll apply this equation to find the electric field strength at point P away from the negatively charged particle. From there, it's just a plug and chug to calculate the electric field strength. Notice how I changed centimeters to meters. The magnitude of the electric field is 3 times 10 to the 5th Newton per Coulomb, and the direction is towards the negative charged particle because electric fields point inward towards negative particles. If it were a positive charged particle, the magnitude would be the same, but the direction of the electric field points away from the positive charged particle. Now let's do an example with two charged particles and calculate the electric field at point P labeled. In this example, we have two charged particles are separated by a distance of 10 centimeters. One has a charge of -20 microcoulombs and the other has a charge of +50 microcoulombs. We want to first determine the direction and magnitude of the electric field at point P between the two charges, that is 2 centimeters from the negative charge. Now, we'll approach this problem the same way we calculated the electric force with multiple charged particles, presented by using the superposition principle, meaning first we'll just ignore charge 2 to calculate the electric field strength at point P caused by charge 1. Then vice versa, with ignoring charge 1, and we'll calculate the electric field at point P due to charge 2. So that means you have to use the electric field equation twice. Notice the direction for both are to the left, because charge 1 is negative, so E1 points towards charge 1, and charge 2 is positive, so E2 points away from charge 2. Let's plug and chug E1 first. Notice that I changed microcoulombs to coulombs and centimeters to meters. And then we get 5.6 times 10 to the 8 newtons per coulomb. For E2, we plug and chug to get 7 times 10 to the 7th newtons per coulomb. Now, since both vectors are pointing to the left, we just add E1 plus E2, and we get 6.3 times 10 to the 8th Newton Coulomb as the magnitude of the electric field, and the direction is to the left. Now for part B. If we have an electron, which has a mass of 9.11 times 10 to the -31 kilograms, and it's placed at rest at point P, and then released, what is its initial acceleration, direction, and magnitude? To attack this problem, we'll first start with this equation, but we'll rearrange it to solve for F. And then from there, we can apply Newton's second law, which is F equals ma. And now we can rearrange the equation to solve for acceleration. We plug in the magnitude of the electric field we solved for earlier, the charge and mass of the electron, to get the acceleration of the electron to be 1.1 times 10 to the 20 meters per second squared. Whew, that is fast. Now for the direction, electrons or negatively charged particles move against electric field lines, whereas protons or positive charged particles move with the electric field lines. So for an electron, it's moving to the right, which is against the net electric field. Just to recap the direction of the electric field, for positive, it's outward, and for negative, the electric field points inward as individual charged particles. But if you have two charged particles present, the artistic pictorial of the electric field lines look like this. The positive outward and towards the negative particle inward. Now if you have two parallel plates with opposite charges, the electric field lines are straight across. Notice that the electric field line spacing are equal. So this means that the strength is constant throughout the middle of the two plates. And it only starts to bow out a little bit towards the end of the plates.